So let's maybe just briefly recap where we are, right? So what we are doing and where we are headed, right? So that's something which I want to get started with today, right? So if you recall what we discussed at the beginning to motivate the need for this course itself, right? So if we consider a dynamic system or a plant to which we provide an input u of t and we obtain an output y of t. So let us say, I want to regulate the output of the system, right? So to a desired value, right? So for example, let's say the temperature of air in this room, right? So we give what is called as a reference input. Okay, so the reference input tells us, what is the desired value of y of t. Okay, so that's what we have, right? And then what we do is the following. We essentially look at the output, sense it, give it as a feedback, and then we compare with what we want with what we have, right? And then we get an error. Let's say we denote by E of t, and this error is passed through a controller which then calculates the control input. Okay, then we call this input as a control input. Okay, so this becomes what is called as a control input, because once the controller calculates what is the input that is provided to the system, the input to the system is called as the control input, right? So this is what we are our overall objective of this course is concerned, right? So we want to learn how to design this closed loop feedback system, control system, right? So that we can regulate the output of the system to whatever value we want. Okay, this is what is called as an output regulation problem. Okay, so that's what we want to do in this particular course. Okay, and that's the concept and the corresponding theory is what we want to learn, right? And what are we doing? Right, so right now, okay, so right now where we are is the following. We are in the system block. Okay, so the class of systems that we are considering are the class of systems is SISO, linear time invariant, causal, dynamic systems. Okay. Okay, once again, I'm just recapping the big picture, because after these many lectures, we have to see where we are, right? So that's my objective to begin with this discussion today, right? So we are dealing with SISO, LTA, causal, dynamic systems. Okay, that's the class of systems that we are going to look at, and we are going to study these systems by using a class of models, right? That we call as a lump parameter, okay, dynamic, okay, deterministic, at least in this course, right? So deterministic, right, continuous time models. Okay, continuous time mathematical models. Okay, so that's what we want to use to study, right, these systems, study the response of these systems. Of course, one may ask the question, hey, is this class of system a very small system in the whole space of dynamic systems? Of course it is, right? So that is it is a small subset, right? But nonetheless, it's a very useful subset. Okay, so we can see that in practice, in many engineering applications that involves dynamic systems, we would try to visualize a process or a practical system through this prism, okay, of SISO, not only SISO, we can have MIMO, but linear time invariant causal dynamic systems, okay. So that's something which we will see that happens very frequently, okay. So it's a very useful, framework to learn, okay. And we essentially approximate the system's response using this class of mathematical models. This takes the form, typically takes the form of linear ODEs with constant coefficients, okay. So that's why, like all this time, like we have been looking at linear ordinary differential equations with constant coefficients. Because it so turns out that, like if I study this class of systems using this class of mathematical models, by and large the representation comes out as a linear ODE with constant coefficients, okay. That's the theory. Then what did we do once we had this, like we applied the Laplace transform to obtain the transfer function representation, okay. So that's what we have done till now. Then we have looked at properties or characteristics of the transfer function, like what are the poles of the transfer function, what are the zeros of the transfer function, and then like what are the implications of poles and zeros, right. So that's something which we have looked at, right. So as far as transfer functions are concerned, like we had poles and then we had zeros. We saw that poles are directly correlated to the stability of the system, right. What we the notion of stability that we are following till now is what is called as bounded input, bounded output stability, right. So the location of poles is directly tied to Biot stability, right. For Biot stability, we want all poles to be in the left of complex plane, right. So that's the idea. And zeros essentially affect the dynamic response, right. So that's something which we have seen. Okay, and we looked at what are called non-minimum phase zeros and their effects when they will come in and so on, right, yesterday. Okay, so that's where we are, right. So as far as this particular course is concerned, we are still here. Okay, then what we will do is that like we will go to controller block. Okay, by next week, in a few, maybe 2 or 3 classes, we look at what are the potential choices for this controller block, and then like we would learn how to put them together and design. Okay, so that's going to be the entire course, right. So then once we learn the design tools, we will apply it to practical problems, we will start working out case studies, and when you go to the lab, you will see how it's applied to real systems, right. So yeah, and then we will learn what is the overall use of the theory that we are learning in this course, how it can be used in practice, and then what is the impact, right. So we will get the big picture, right, towards the end of this course. Okay, so that's what we are going to do. So so if I want to have an equivalent block diagram, of course here we also looked at the fact that like I can have sensor dynamics coming in, we also have actuator dynamics coming in, right. We can have disturbances being applied to the system, right, and so on. Okay, so all these factors can come into the system's play, right. So the same block diagram, this is what is called as essentially a closed loop control system with negative feedback, right. So once again, I'm just recapping whatever we have already discussed. Okay, so now once we have this, right, so if you want to draw a similar block diagram, okay, in once we want to essentially analyze these blocks with the corresponding transfer functions, right, and we want to draw a similar block diagram once we transform to the complex domain or the S domain from the time domain, how do we do that? Okay, so that's something which I'm going to discuss now, then we will go to performance analysis, right. So if I want to draw a similar diagram, let's say we go to the complex domain, right, I'm going to draw essentially the same elements. So the plant transfer function, let's say we call it as P of S. Okay, so the input, control input, let's say we call it as U of S, and then like output we call as Y of S. Okay, and the Laplace transform of the reference input, let's say we call it as R of S, right? And let us say, like we have some mapping in the feedback path, okay, without loss of generality. So let us say, like I put a mapping in the feedback path, which we call as H of S, right? So if H of S is 1, we have what is called as unity feedback, right? So we discussed what is called as unity feedback and non-unity feedback. I'm going to come to that once again, right? Let me draw this diagram. What does H of S indicate? H of S is just a visualization of any mapping that comes in the feedback path, okay? Then let's say, like we call this error, Laplace transform the error as E of S. Let's say we call the function that comes to the summing junction as W of S, because sometimes, like if H of S is not 1, let's say I put a filter in the feedback path to filter out the sensor's noise and so on, right? The output signal is anyway modified. The modified signal, let's call the transform signal is called W of S, right? So let's say, like I pass this error through a controller block. Let's say I call the controller transfer function as C of S, and then I go here. Okay, for the time being, let's say we neglect actuator dynamics and so on. Okay, so let us say this is my corresponding block diagram in the complex domain, right? The same visualization. So let's see where we are headed with this, right? So I hope it's clear how we got these two diagrams, right? I'm just mapping it. H of S is indicative of any mapping that can happen in the feedback path. Okay, like let me write the explanation. Okay, it's the feedback path transfer function. See, let me give you an example, right? So let us say, like I have a system, right? And let us say, like I have some sensor to measure the output. Okay, let's say the sensor signal is noisy. Before feeding it back, I may put a low pass filter. The low pass filter may have some transfer function, right? That I embed as H of S, if it's important. Okay, the question we need to ask ourselves is that, like, is that important for us to consider, right? Then we put it in. Okay, in some applications, okay, it depends on how you visualize. Okay, so in some applications, let's say, like I want to control the displacement of an object, but the sensor I have measures the speed. If I want to get the displacement, I need to integrate. Then what I can do is that I can say my output is speed, okay, to be consistent with my sensor measurement, and in the feedback path I integrate. So if I integrate, the H of S happens to be 1 by S. So then I put 1 by S as H of S. Okay, you can do it anywhere, right? So it's just a matter of visualization, right? So H of S indicates any mapping that you can have in the dynamic mapping you can have in the feedback path. Okay, so if H of S is 1, we call as unity feedback. Okay, so we should be familiar with all these terms. Okay, if in any problem, if I say consider unity feedback, that means that H of S is 1. Okay, that transfer function becomes 1. Okay, so obviously if H of S is not 1, it is called non-unity feedback. All right, I'm sure this terminology is clear, right? Okay, fine. Okay, now let's do some simple algebra here. Like please stop me once again if there are any questions. Okay. So let's do some simple algebra here. Okay, so the advantage with going to the complex domain and drawing this block diagram is that if you take the output of any block, see for example, let's say we consider this plant block. Okay, the output signal at the plant block is capital Y of S, right? And that's going to be the product of the block transfer function times the input to the block. Okay, the input signal to the block is capital U of S. Okay, you take that, you multiply with the corresponding block transfer function, you will get the output signal. Okay, so that's the convenience we get, right, once we go to this representation. Okay, so obviously Y of S is going to be P times U of S, right? What is U of S then? U of s is the output coming from the controller block. It's going to be the controller transfer function times the input to the controller block. So we are going to have it as C of s times E of s, right? And then what is E of s? Let me just change the order of multiplication. Okay, C of s, P of s. I can do it because like I'm working with scalar signals, right? So these are scalar valued functions, so I can just swap the order. If you work with MIMO systems, you need to be careful, okay, because these will be matrices, okay. So in general, if you have two matrices A and B, A times B is not equal to B times A, right? Matrices do not commute in general, right? As far as multiplication is concerned, we need to be careful, right? Okay. So C times P of s, what is E of s now? R of s minus W of s, okay. I'm just writing in the same stretch, okay. So this implies that Y of s is going to be equal to C of s, P of s times R of s, okay, minus C of s, P of s. What is W of s? H of s times Y of s, right? Do you agree? Okay. So usually, okay, G of s is defined as C of s times P of s. Okay, that is the what we call as G of s is essentially the product of all the transfer functions that come in the forward path. Okay, this is the forward path, right? So essentially, whatever comes in the forward path, you take all the transfer functions and then multiply them. That's just a notation. Okay, just a definition, right? So let's say we call this as G of s. What happens here? So you get Y of s to be equal to G of s R of s minus G of s H of s times Y of s. Correct? So you see that Y of s is common on both sides. So you take it to the other side. So you will get 1 plus G of s H of s Y of s is equal to G of s times R of s, right? So this implies that Y of s divided by R of s is going to be equal to G of s divided by 1 plus G of s H of s. Oops. How did I do? Yeah. Okay. So this is what is called as the closed loop transfer function. Okay, why is it called as a closed loop transfer function? Suppose, you know, like I draw a big block, okay, around this all, which encloses all these elements, right? Okay, so I'm just drawing a big block which essentially encloses all the elements in the closed loop, right? So what happens is that like I get a block, I'm just redrawing the block here, okay, and what is the input to the block? R of s, right? Correct? What is the output from the block? Y of s, right? And what is the transfer function that we have got? It is G of s divided by 1 plus G of s H of s. Okay. So now you understand why it's called as a closed loop transfer function, right? You encompass all the elements in the closed loop system using one block, okay, with R of s being the input to the block and Y of s being the output. G of s by 1 plus G of s becomes the transfer function. Yes. We'll come there. Okay, we'll discuss that point. Okay, so let me repeat his question. So we are assuming zero initial conditions, right? When we deal with the transfer function representation, right, on all locations, right? Question is that how is it going to affect the response? Okay, we are going to come to that question. Okay, yes.
You said something about matrices and how.
Yeah, so if you have a MIMO system, okay, like I wanted to alert you regarding that fact. Suppose if you had a MIMO system, like let's just do an aside, right? So just to convey what happens, so let me scroll up. Okay, suppose if you had a memo system, right? What will happen is that all these elements will become vectors and matrices. Okay, like I'm using a tilde to represent a vector and a matrix. Suppose y is a vector, y of s will be a vector, right? And let's say u is also a vector, u of s will be a vector once again. Then what you will have is that you will have a transfer function matrix. Okay, let's say you have 3 inputs and 2 outputs. You will have a 2 by 3 matrix for the transfer function. So the transfer function will no longer be a scalar valued function. It will be a matrix valued function of s. Okay, it will still be a function of s, but then the mapping will be giving you a matrix. So the moment you have a matrix, let us say your u of s, you write it as c of s times e of s. What did I do? Right? Oh, sorry. Yeah, e of s. Then if you substitute it here, what will happen is that you will get p of s, c of s times e of s. Okay? I just wanted to alert you to the fact that you can't write in this case p and c are matrices, right? I can just swap the order. That's why I just want to alert you. Okay? Here, in many textbooks, you will see, like this is written in this manner so that you go along the path, right? But the order of multiplication matters when you go to the memo system, right? See, here you can observe what I did, right? I wrote p and c, I just swapped it to c of s, p of s here, right, in this step.
That wasn't in test. You didn't do that in test.
I didn't do it that's just a convention, right? So you can keep it p of s times c of s, right? So that's also okay, right? So see, the reason I did it is because like c of s times p of s means you multiply as you go along, right? This path. Okay, that was the intention, right? So you could have kept it p of s times c of s. But what I wanted to alert you there is that if you have a memo system, obviously this is not in general equal to c of s, p of s, e of s, right? You can't do that. You can just arbitrarily commute matrices, right, during multiplication. That's exactly what I wanted to do. Is it fine? Yeah. So, so this is the closed loop transfer function. Okay, so that's what is called as a closed loop transfer function. I hope this is pretty simple, right? So I think definition should be clear to us. Now the poles of the closed loop transfer function. So I am just going to abbreviate the closed loop transfer function as CLTF. Okay, just for like. Not keeping on writing closed loop transfer function all the time, I am just going to put CLTF as an abbreviation. Okay, so the closed loop transfer function are called closed loop poles. Okay, fine, and obviously the zeros of the closed loop transfer function are called closed loop zeros. Okay, right? These are some terms. So how do you calculate the closed loop transfer function? Closed loop poles. Once again, like you give me any transfer function, poles are the roots of the denominator polynomial. Period. Okay, there is no confusion in that. So what is the denominator polynomial in the closed loop transfer function? You look at the denominator, what do you have? 1 plus g of s h of s, right? So if you want to calculate the closed loop poles, we just solve 1 plus g of s h of s equals 0. This is what is called as the closed loop characteristic equation. Okay, so we should remember all these terms because we are going to use them repeatedly. Okay, characteristic. Okay. Characteristic equation. Okay. Okay. So this is what is called as a closed loop characteristic equation. Why is it significant? The roots of this equation are the closed loop poles. And why am I interested in closed loop poles? Because when I design a closed loop system, obviously first the closed loop system has to be stable, right? See, when will the closed loop system be stable? When all the closed loop poles lie in the left of complex plane. That's why we are interested in closed loop poles, right? So, and the polynomial one plus g of s h of s is called as the closed loop characteristic polynomial. Okay, so that's what it is called as. Okay, closed loop characteristic polynomial. Okay, so that's 1 plus g of s h of s. So the roots of the closed loop characteristic polynomial are the closed loop poles. Okay, so please remember these terms.